In this set of lecture notes, I want to briefly cover kinetic energy. Keyword, briefly. We're going to come back to this idea and talk more about kinetic energy when we talk about other types of energy. So right now, we're only going to use this idea to apply to collisions. So first of all, kinetic energy is defined as 1/2 mv squared. So that's the equation for it. So m, of course, is the mass, and v in this case is speed. Now, we'll talk more about it later, but any kind of energy in general is a scalar. So this is not something that we need to start thinking about direction, really, because it's a scalar, so no direction. And also this v here, mathematically speaking, is squared, so even if you plug in a negative number, it's still going to end up being positive. So again, we'll talk more about scalars and energies in the next set of lecture notes. But for now, let's just say that what this amounts to is that you don't have to worry about components. Or direction, for that matter. Okay, so just for the time being, as applied to collisions, just think of this as plugging in speed. Units of kinetic energy, and any energy for that matter, are called joules. So a joule can be written as either Newton times meter or kilogram meter squared over second squared. And of course, like a lot of our other units, it's named after a guy named Joule who actually first discovered the equivalence of heat and work. We'll address that later too. Okay, so what does this have to do with collisions? Well, if you remember, we talked about classification of collisions. And we stated that there were 3 different kinds. So there was a perfectly elastic collision, partially elastic, or we can also call that partially inelastic. Okay, and then perfectly inelastic. And so we were talking about how for all 3 of these collisions, we would have conservation of momentum, right? So P total is conserved, okay? We also talked about how for this top 2 collisions, we have no coupling. And for the perfectly inelastic collision, we would have coupling. But then I said that in order for us to distinguish between perfectly elastic and partially elastic collision, we need to have some knowledge of kinetic energy. So literally, the distinction in determining which kind of collision that is, in terms of comparing perfectly elastic and partially elastic collision, it's not about momentum, it's not about coupling, it's about energy. Okay, so for perfectly elastic collision, I'll write it over here, change in total kinetic energy is equal to 0. And for partially elastic, change in total kinetic energy is less than 0. For inelastic, we also have change in total kinetic energy is less than 0. Okay, but that's not a determining factor there, because for perfectly inelastic collision, you would just see that the objects stick together, and then you don't even have to do any additional work there. Okay, now notice that I am not saying in any of these cases that change in total kinetic energy is greater than 0. That can only happen if there is some external influence, some external input of work, or some unbalanced external force that's happening. And that's also not something that we need to address right now, because we were saying how momentum is conserved only if there are no unbalanced external forces. Okay, so we're not going to consider that. So right now, we're only saying that either total kinetic energy of the system is going to stay constant or it's going to decrease. Okay, so we don't have any other options there. So recall that the example that we did in the previous set of notes, right? We had two objects there, A and B, that were moving towards each other and colliding head-on, right? We had both masses, mass A and mass B, and we said that the speeds were both 2 meters per second before collision. After these objects have collided, they're moving in the direction opposite of the original direction of travel, right? And then we were given the final velocity of object B, or final speed rather, and we had to calculate final velocity of object A. And we did that. We calculated the speed to be 0.4 meters per second, right? So look at the previous set of lecture notes. And then we said obviously that the object A was moving to the left, so that's why I'm writing these values as speeds, not velocities. And I should label these guys as V initial A, and this is V initial B. So let's see how the energy stuff works. Obviously, these objects are not coupling to each other, right? So this could not be inelastic collision. So it has to be one of the first two kinds. So we're going to check what happens with kinetic energy. I'm going to calculate total initial kinetic energy. So this is going to be 1/2 ma VIA squared plus 1/2 mb VIB squared. Okay, so obviously we have all of these values. We can just plug them in. Okay, we have the masses and we have the speeds. Again, in this case, velocities do not matter, only the speeds. Okay, so if I crunch all of these numbers, I get 1.6 joules. So this is the total initial kinetic energy. And then let's calculate total final kinetic energy. Okay, so I'm gonna basically write it the same exact way, but use the final values for speeds. Okay, plug everything in again. So this is the one we calculated to be 0.4 meters per second. Okay, be careful with all of those squares. And this is still 2 meters per second. Okay, so I get 0.64 joules. So notice right away that the total kinetic energy at the end is not the same as total kinetic energy in the beginning. Okay, so let's calculate delta K total. So this is going to be the total final kinetic energy minus the total initial kinetic energy. So 0.64 joules minus 1.6 joules gives us negative 0.96 joules. Since we got this change in kinetic energy to be less than 0, this tells us that this is a partially elastic collision, or you can also say partially inelastic collision. So that's how you can classify collisions. If there is no coupling, you have to go through this procedure, through this process of figuring out what delta K total is. Okay? So then where does this energy go? We obviously have not talked about energy conservation yet, but basically this value here, this tells us that this is how much energy was lost. Okay, so we'll revisit this idea later, but but I'm just going to tell you really quickly. When we say lost, it doesn't mean destroyed. It means this energy left the system. And typically, when we are talking about collisions and we're talking about kinetic energy leaving the system, this means that this energy converted to heat, sound, light, or deformation. So for mechanical systems, you're probably not really going to deal with light. It's not like after a collision, these parts are going to emit light. But heat, or we can also talk about thermal energy. Let me write that down and then we'll discuss what the difference is. Thermal energy. So you can say heat or thermal energy for now. Okay. Sound, that's kind of self-explanatory. Deformation, well, that's also kind of self-explanatory, right? So think about like real automobile collision. What happens when the two cars collide? They're going to deform, right? So that requires energy. So that's where that energy could go. Okay. So this is actually pretty much all you need to know for kinetic energy as applicable to collisions. I'm just going to mention one other thing, that when you have perfectly elastic collisions, a lot of times, instead of writing delta K total is equal to 0, it's more beneficial to write K total initial is equal to K total final. So basically, you can also refer to this as conservation of kinetic energy. I'm not going to box this because it's not really a law of conservation of kinetic energy. Now, conservation of energy, that's a different story, but we'll get to that. But specifically for perfectly elastic collisions, it is quite possible that you would have to use that idea. So you already know how to use momentum conservation, right? So P total initial equals P total final, right? So that's our momentum conservation. In more complicated cases, you would also have to use a conservation of kinetic energy as well. So for example, if a problem states that two objects collide and collision is perfectly elastic, you can actually go to writing this conservation of kinetic energy right away and then use that as one of your equations necessary to solve for whatever it is that you're solving for. And we'll obviously revisit this idea of kinetic energy later and go into more depth of what it actually means and what it does. So for now, we're only using this to figure out the type of collision.